There's a new brewery on an old site, so they're running an old brewery and a new brewery side by side. They had a major fire, which burnt out the fermentation block and therefore closed the new brewery, so ended up not having to start up straight away, so it gave me a lot more training time. I ended up having training sessions with all the suppliers, including Whitman, and it's very, very thorough. I found it very, very useful. So all the main suppliers, Steinecker, everyone, spent a lot of time with them. It was good. We also use Whitman equipment when we transferred the Romford brewery to China, and we installed Whitman there. Then after that, it's always been Halfman's. If you know these names, Halfman's are part of Pentair. And then we did a job, Sam and I did some work in for Heineken East Timor where we used Union Engineering plant. All of those companies became Pentair. So that's it, they're all gone, they're all Pentair now. More recently, I've been investigating CO2 plant for smaller breweries. That's what we're talking about today. So, what are the properties that are beneficial to brewers? It's obviously naturally occurring in fermentation process. Used in keg, bottle, or can. And we might want to make it a bit more bubbly, so we add CO2 to fizz up those products, whereas cask you probably don't need so much. It's used for blanketing beer to keep the O2 out. Stop your start oxidized to oxidized, isn't that? And it tends to counteract aerobic microbes because basically you're removing air, you're keeping the air away. So it's logical, really. And where is CO2 recovered from? Now, a lot of these might surprise you. CO2 can be collected from boiler flue gases. We had a chat, we couldn't think of any breweries in the UK that do that. Soft drinks, maybe. Soft drinks are likely to. But in Australia, Africa and the Far East, it's quite a common thing to take your gases off the boilers. In fact, talked about brewery, Cooper's Brewery in Adelaide. They actually got most of their CO2 from the local power plant, and that's what happened there. The local authority closed the fuel-based steam radiant system and went for electric boilers. No more CO2. I'll put there, if you want to learn about flue gas separation, then that's another talk. That's not one for today. There is a tendency today as well to convert boilers from fossil fuels to electric heating. In fact, if you go to Sarco's works, they are actually converting their own boiler there to electric. And I say, in this case, no CO2 is produced, so it's not much good for us. So for what we're talking about today, we're talking about CO2 collected from fermenters. So, keys to a successful CO2 recovery system: have an adequate and continuous supply of CO2. If you're brewing 1 day a week, not really worth it. If you're brewing 4 days a week, yes, getting somewhere near there. But basically, you want a continuous supply of CO2. You've got to eliminate all the water, so try and stop getting in there in the first place. And obviously, you want to eliminate air from your CO2. We'll come to that in a minute. And all the above will give you a better CO2 availability for collection. So, what I thought I'd do is talk through a large-scale CO2 plant, which is why then they're downsized mainly for smaller plants. When I was starting in the industry, you had to be 1 million hectolitres at least to have a CO2 collection plant. It wasn't feasibly economically worthwhile. main reason for that was we got our CO2 very, very cheaply from the distillers. And I worked for Watney's. We owned the distilling company. Guinness owned the distilling company. CO2 was freely available. You know, it was a waste product to the distillers, so it came on the market very cheaply. Nowadays, you pay for it all. You'll see in a minute what that means. I picked a diagram here from a Shanghai company. In fact, if you look at all Pentair's literature, it's the same diagram, it's just the labels are different. But there's quite a slightly neater drawing with better labelling, so I've chosen this one. And I've put it into two, gas collection and liquefaction. So let's start off with gas collection. CO2 is collected once its purity has reached a minimum level expected by the plant manufacturer. That's about 95% pure, 5% oxygen. So that's coming off the fermenter, and you put it through a foam trap to get rid of your fog. The fog, you have to get rid of it somewhere before you liquefy it. So that's a good way of doing it. You put it in a tank, you wash water over it, which takes the foam out, which you drain off from time to time. And then basically go into a gas balloon, which John mentioned. That balloon has two purposes really. It's a reservoir, yes, but it actually feeds onto your compressor. So you have to have a bit of a positive pressure feeding onto the compressor. You don't want it to come straight off the fermenter at no pressure at all. The other thing is it minimises the back pressure onto your fermenter. When I started at our brewery, so we wanted very low, less than 7 psi top pressure on your fermenters. And we went to lager, they want 1 bar to keep a bit of fizz in the beer. So you put in a balloon there to control both, so it seems to keep the feed pressure down and to give you a bit of a boost onto your compressor. And you've got a scrubber then, so you've got this slightly raised pressure, dirty CO2, and you try to get rid of soluble contaminants first, which is ethanol, and that's by washing with water. Basically, it's the same thing as foam trap, it's just a bit more, you go over a tortuous route, and you remove these ethanol and other contaminants which go to drain. So with that there now, I'm coming down onto this side. Scrub gas is collected in it's compressed to roughly above 40 bar G. That's the standard for most big scale CO2 plants. They use a multi-stage compressor, and sulfur impurities come out in the interstage cleaners around the compressor. So high pressure CO2 is then cleaned to remove other impurities, in this case using a carbon filter. That's those twin, the first two twin elements there. So I'd like to show you with the pointer, really won't do it on the screen. That takes out odours, unpleasant taints. And then it passes through the other two vertical vessels here, which are dryers. Now these are adiabatic adsorption dryers. They work adiabatically, but adsorption dryers, which actually use usually ceramic discs or ceramic shapes like Pringles, for example, that sort of shape, saddle shape, and they actually collect the water, the moisture into the pores of those ceramic discs. Then every now and again you dry it out. So that's why we've got two. We run one and we dry the other one, so it keeps it going continuously. Okay, so now we've got CO2 at 40 bar. It's relatively clean, and basically you're then trying to cool it down. So another table in a minute, which I'll show us a chart in a minute. I'll show you, but you'll see why we have to do it at 40 bar. We use here, generally it will have its own inbuilt ammonia refrigeration plant, or Freon, or whatever was the fashion of the day. But nowadays more likely ammonia to get you cooling. So there we go. Very little oxygen, because you can use a stripper which actually removes all the remaining traces of the oxygen. Here's a phase diagram this is what I'd like to show you. If you look at 40 bar, down there you're talking at around about 0 Celsius if you wanted to go into the liquid phase. Lower, your temperature is going to go right down below 0. That's why we're keeping the pressure up to 40 bar. Got your triple point down there, that's ionized liquid phase and gaseous phase all at minus 50 something, minus 55 degrees. It's quite an interesting chart, which we'll see again when we talk about the smaller plants. Why do people go for CO2 plants these days? Why can't we just buy Air Liquide or whoever? And the reason is the cost. I've got these figures from a small brewery, 25,000 hectolitre annum brewery, and they're paying between 500 and 600 pounds per tonne of CO2 plus energy surcharge. And that surcharge at the moment can be as much as £285 per tonne. So you're now talking about £835. You might be saying, oh, we don't pay as much as that. Well, price, that's cheap. So it depends where you are. You can do a deal, whatever. But, I mean, does anyone here have any ideas of prices? Is that typical for what you're paying? Don't know. I can tell you it's a lot of money. When I was in London, breweries in London, we probably paid £150 a tonne, something like that. It's reasonably cheap. Well, you know, you don't need to bother if you're a small brewery. Nowadays, you've got to seriously think about it. So the cost of recovered CO2 is significantly lower than CO2 purchased in liquefied form, even allowing for the capital installation costs, maintenance and depreciation. We've been talking to people like Dallum. I imagine Sam will say the same with his Gigabyte Pro. In that payback period, 1.5 to 2 years maybe, or something like this. That's pretty damn good as far as I'm concerned, especially when you can't rely on the supply in a couple of years' time. How do you put it yourself? So your main operating costs are electricity usage and small costs for water use for the fog vessel and minor maintenance, filter beds, lubricants, etc. So it's a fairly low maintenance operation. I was speaking to one brewery and said that their biggest problem at the moment is actually getting a maker's man to come out and give them a help. So there's very few of these made in the UK at the moment. So most of them imported. And that applies to big plants as well. I don't know of too many English-made CO2 collection plants. And I just added this on the bottom. Oh, let's stick the plant here. It's going to cost me 20 grand. Stick the plant down. That's it. We can use it. But no, just have a look at safety equipment. And you know what? In fermentation, you're talking about the CO2 is toxic and heavier than air, and you're more likely to die from asphyxiation than you are from toxicity. So we tend to use low-level extraction, maybe big vents on the ground level to remove it. You've got to watch out about drains and cellars below your fermentation area. And this was a big problem when they built Carlsbrook Brewery in Northampton, where the vessels were actually, the fermenters were actually quite wide down. And more recently, you've had to wear, if you go into the fermentation cellars there, you wear a CO2 detector when you go in there. That's a requirement on the site. That's common in many big breweries now. So, as well as gas detectors, which will have a preset alarm to say it's getting dangerous or don't go in, danger of death. You've also got to have your RAMs, got to bring your risk assessment method statement to go anywhere near these plants to do maintenance. You can't go inside a vessel, for example, without having RAMs. And the same applies, I think, to when you're working on a CO2 collection plant. If it's in a small room, that room is a confined space. I've seen some of these in open areas, which is a lot better, but they can produce a lot of gas quite quickly. CO2 is considered odourless, and it is odourless when it's condensed like this. I mean, in a brewery, if you brush off the top of the fermenter, you can smell the beer products, you can smell the beer, and it gives you a bit of a sharp burning sensation in your nose. When it's like this, when it's high pressure or pure, you can't smell it, and all of a sudden you're overcome by the gas, and cheerio. So what about the CO2 recovery plant room? Especially if it is in its own room. Your CO2 monitoring equipment is still essential. Visual alarms, what we'd like to see. As a designer, I like to see an alarm on the outside of the room. Also like to see a repeater maybe in the gatehouse, so if you're not there, the guy in the gatehouse can say, call someone in and say there's a problem with the alarm in the CO2 recovery area, or to warn people. But the more people that know that there's a problem, the safer you're going to be. So make sure everyone is properly trained. Again, low-level extract fans are required ducted to the outside, not to the room next door, to the outside, and so it can be blown away. You know, end up forming another problem area next door to the plant. If it's linked to your SCADA system, these medium-sized breweries are going to be, stick the repeater in the gatehouse, or on your head brewer or chief engineer's iPhone, so he knows what's going on at the site. Never cut corners when it comes to safety, price it in. That's basically what I'm trying to get at here. It's part of the cost of putting the plant in. So it's got on to small and medium-sized breweries. No longer a CO2 recovery plant is the sole preserve of the larger output breweries. As I said earlier, 1 million hectolitre per annum was about the minimum size for a CO2 recovery plant until probably 10-15 years ago. So everyone relied on cryo tankers to deliver the liquid CO2 from wherever, from your air products, your gas supply, or from distillers in liquid form. And then we got CO2, I mean, was it 3 or 4 years ago, just before COVID, we started getting shortages of CO2 because the fertilizer plants were in their feedstock from the oil and gas industry. So suddenly we have no CO2. Everyone panics. And a lot of these small-scale plants came out of that panic. They started going into 4 or 5, just pre-COVID until now. They've got a small footprint, so they go in quite easily into a small brewery. And I think we can prove now they can be self-sufficient. I think those that put them in have said that they are worthwhile. It's definitely a good investment. I mean, we learn more as we go along about whether they are durable, they keep going for long periods of time. But I think at the moment everyone's saying do it, go. How much recovered CO2 will I use? Well, this depends on how much CO2 you buy in at the moment. If you're buying several tonnes a week, your plant needs to at least cover that amount, plus a bit more. So if you're a cask only brewery, you probably won't need so much, but you're still producing CO2, so you could collect that and sell it in cylinders or something for other people. You can use it for line purging, particularly in your beer. I know a cask brewer, it's the biggest cask brewer in the country a few years ago, wasn't it, Jim? And we ended up putting a CO2 plant in there because they could not quite get the mouthfeel they wanted for the CO2 plant. So they ended up using CO2 to tickle even though it's a cask beer. And you'll find this happens quite a lot. If you're on large and small packs, so your keg, bottling and canning, and CO2 recovery plant will pay for itself very, very quickly. The sizing techniques. Sizing a CO2 recovery plant to a large extent is in your own hands. You know your current production programs, length of your fermentation processes, gravities, etc. And you can actually do this yourself and calculate in fine detail how much you're going to collect. But don't forget to account for future expansion. So you can do all these things if you want to. I'm suggesting maybe you don't. And but don't forget, if you want to expand, you think, oh, let's do an extra days per in next quarter or something like that. You have to take that into account. So, this is working very quickly. So it's quite difficult to accurately size a CO2 recovery system in a normal multi-SKU brewery. It's very good if you're a Budweiser, nothing but Budweiser, or as I've done overseas, a totally 5% lager, 24/7. It's much easier to size, much easier to do it. If you're doing, 2 tanks of ale, 3 of IPA, 2 of lager, whatever, it's much harder to actually size the plant. So what we tend to do, that's what we just said, so the more consistent your brewing plant is to size a recovery plant. But most brewers make it estimated based on custom and practice or on the advice of others. Okay, so I'm just going to show you a couple of those things in a second. Let's go back like that. That's the back. So assuming you're collecting for fermenters only, the following slides will give a good idea of what to expect, as will the brochures from the main small-scale CO2 recovery plant manufacturers. Okay, this is a graph from lifefermentedwordpress.com. It's basically it's CO2 produced versus specific gravity. And it's for an 18.9, that's a 5 US gallon batch, 18.9 litres. So I've did a quick sum on this to see how it works. I've put that line across, 75% attenuation and 5 plateau. Sorry, not 5 plateau, 5 ABV, so 1048. So if you look at what I've done, you're taking a curve 1048, so attenuation, and you get 0.7 kilograms of CO2 over there. So 1 hectolitre, 100 over the 18.9 litres, times 0.7 gives you 3.7 kilograms per hectolitre of CO2. Now that isn't a bad estimate overall. I previously worked for several iterations of NIRAS in the past, so as Danbrew, Bjorn Krobo, Electia, and now they've all gone, it's now NIRAS. But we used to use 500 kilograms per hour of CO2 for every million hectolitres per annum of beer produced, sales gravity beer. And if you use that, it's equivalent to about 3.6 kilograms per hour, and that's fairly similar to the table we found on the page before for a small scale. So I've used that rule of thumb there and converted that for three sizes of brewery: 25,000 hectolitres per annum, 15,000, 5,000. You have to trust my maths. It's on my telephone. But basically, 25,000 hectolitres per annum brewery would produce a collectible amount of CO2 of 12.5 kilograms per hour. That's and scaled down there. It's not a truly linear relationship. Not truly linear, so they may be modified for scale. So on the next page, I've got a couple of manufacturers. I've got Dallam, and I've got an American company called Chart Industries. And you can see that 25,000 was 12.5. One on the page before, 25,000 was 12.5. Dallam say 15 kilograms per hour. I think that's reasonable. I think that's a reasonable figure. So talk to the manufacturers and see what they say. Just round it up a little bit if you like. Get the next size up if you need to. But, I mean, you don't want to oversize it and run it lightly loaded. So that's the sort of figure. That's the formula for calculating the amount of CO2. So if you want to do a bit of homework, take a mole of glucose, produce 2 moles of alcohol, that's 2 moles of CO2. But don't forget the CO2 retained in the green beer and the stuff that's vented off to atmosphere because it's not pure enough comes out of that equation as well. Okay, so I don't bother with it, I just use the main ones. I've given a link to a paper by Jaime Gerardo, who used to be president of the Master Brewers of America organisation. He's done a very, very good paper. I've got the link to it, so have a look at that link. It's quite good. It also gives quite a few safety things on there as well. It's well worth it. Jaime worked with me at Truman's Brewery, and later went on to Courage's before he went stateside. So he knows the game. But when did you start to collect CO2? Normally, in the initial stage of fermentation, that your vessel will be air at the top and gradually become CO2. So how long before it's 95% pure? And basically, we can do this by trial and error. Test your offtake until it's pure enough, and then send it to your collection plant. When you put multiple brews into one vessel, that will delay it. You can't really get rid of all the air until all the brews are in and a period of time has gone by. Some breweries have their own standard times. So that's with breweries who are now part of AB InBev. They had their standards for things like Miller Genuine Draft and for Peroni beers, and they said we will not collect for at least 24 hours after the tanks are full. So you've got to do what the brand owner says. John Round reckons that 7 hours after the tanks are full, you can start collecting. Right. And I think that's quite a good figure. If you're in your small breweries, have a look, do a test for a couple of beers. Is it 95% pure at that stage? If so, 7 hours is good enough. What you want to try and do is collect as much as possible, obviously. So can put CO2 monitoring equipment in. I've done it in some breweries. It seems to me a waste of time. It's not reliable. And basically, the only problem you've got here is when you're not collecting it, CO2, mixed CO2 and air has to go somewhere else. So, I mean, what they brew used to sink through a hole in the wall, and it just run down, all the foam would run down the side of the building, which is bloody awful for a new brewery. So you end up putting a foam trap on that side. And then when it got to 95%, we click over to the collection plant. That's basically all you're doing really, is getting rid of it to atmosphere, stop it messing your building up, and then collect it when it's ready to be collected. So you need a valve in each vent line to seem a common main to the collection plant. So it is a bit, if you're 6 or 10 FEs, every one of them will need a connection to the vent collection, the CO2 collection line, so that you can turn it on when you're ready to collect. Hence, most brewers prefer the elapsed time method. You want the highest quality CO2 from your plant as it comes into contact with your products, obviously. No aromas and definitely no oxygen. If your plant includes a refrigeration system to liquefy the CO2, then chances are the oxygen entrapment will be eliminated, as both oxygen and nitrogen are not liquefiable at the high temperature needed to liquefy the CO2. And normally a purity level of above 99.95% is achieved from liquefaction. This is a purity grade, this is a standard, and you'll see on there beverage and food both say purity of 99.9% is acceptable for use in a foodstuff or in beverage. Depends really what that 0.1% is. It's pretty nasty because you can get some pretty horrible taints in that from a 0.1% concentration. So most people these days are saying 99.998% pure, but people, that's what they're aiming for. And all the plant goes into that standard, but certainly above 99.99, I would have thought. So you're talking about research level or thereabouts, or certainly way above medical. That's an interesting chart, that. I think lots of people don't realise that we in breweries want a little bit more than what we have to. So there's several makes of small-scale CO2 recovery plant, and because of the time allowed here, I've just picked two of them. We've got Hypro on the left and Dallam on the right. And they have a small footprint. Both of those two plants are the same output. You'll notice one big difference between the two. Dallam one does not have a balloon, and I'll explain that later on.
Nor a condenser.
Sorry?
Nor a condenser.
Nor a condenser. Okay, so this is the Dallam one, and this is their drawing. And basically, what they do, they don't have the foam trap because their compressor is 100% variable drive, so go from 0 to 100% by variable speed. So therefore, feeding pressure from the fermenters can be as low as you want, and you can pick it up and accelerate it up to wherever you want. And that means they don't need a balloon, so they say. It seems plans working, and it seems to be working okay. Personally, I like the balloon. I like having that little bit of a buffer there. But this is what you pay for these days. And then same sort of thing, you've got the scrubber, same scrubber. This is their drawing. I would rather have a 3-stage compressor that looks like a 3-stage compressor on their drawing, but there you go, that's their compressor. The sulfur filter, H2S. And then you've got your dehydrators here, your absorption dehydrators. They use aluminium oxide, which is alumina. and it's perforated, so it's like sintered, so it's full of holes. That's what they use. It's a ceramic. If you're old enough to know what a spark plug looks like, the white on the spark plug is alumina. This is sintered alumina, and that's what they use to adsorb the moisture. So their liquefier is basically using the standard glycol system or whatever around the site. It's very similar. I'll show you that on the chart. Next chart coming up. Collecting into a CO2 tank, which they do not supply, so you know that. So that CO2 tank has to be the tank you use now for your CO2 recovery, or your CO2 usage, or you have to buy a tank. So when you look at their prices, I don't show you any prices, I'm not a salesman, so don't show you any prices, but take into account that you have to supply a CO2 tank in their system. So just the concept, collect CO2 from the fermenting tank using flexible hoses, so snake pit onto your CO2 collection station. Foam traps the same as the main plant. Your impurities, your ethanols and aerosols, etc., removed in this water scrubber as previously. You say there's the desiccant dehydrator, aluminium oxide, and duplex dehydrator regenerates automatically by heating. So the same as the big boys. Dynamic CO2 compressor provides up to 45 bar pressure, and the CO2 condensation takes place at 0 to 5 degrees Celsius plus. Higher boiling point. This makes it unnecessary to use a separate CFC or ammonia cooling system. A glycol ice water or alcohol cooling system can be used. It basically tie it into your own system in the brewery, so not a standalone system. The dry CO2 is condensed using the external coolant source, and the liquid CO2 is continuously distilled in the condenser coil to ensure low oxygen content. Liquid CO2 is pushed with approximately 35 to 40 bar pressure to the storage vessel, where liquid CO2 expands to the storage tank pressure and temperature. And vaporized CO2 from the storage tank is sent back to the compressor, so it's a bit of a feedback loop going back round. That's a bit technical for what we're talking about today. It's and this is their chart. You saw this chart earlier. In their case, 40 bar and 35 degrees Fahrenheit or 2 or 3 degrees Celsius. So you can see you don't need so much coolant capacity to actually liquefy the CO2. That's a conventional one there. 240 psi, which is 16 bar, and minus 26, 27. But that's sort of, the standard one. You need your refrigeration system to be able to knock down fairly cool temperatures. So by making a higher pressure, they can actually allow you to condense it at a higher temperature. A few things they say, oil, chemicals, filters or refrigerants. And their purity is 99.98%. No detectable odor. Oxygen trace is measured in parts per billion, so that's low. So this is all their sales gimmick. So I skim past that quickly. It's the stuff I found on the internet. This is an interesting thing. Talon did a gas collection experiment at a brewery. They won't tell me what size of brewery it is, but it's an ABV of 4.8, so similar to what I was using, and the yield was 3.4 kilograms per hectoliter. So it's quite a similar type of range. This is the Hypro plant. Because of time, I've decided I haven't done too much on this. Just very similar process to the big scale plant. It uses a glycol-based refrigeration system, and there it is there. Produces 6 to 120 kilograms per hour liquid CO2, and it's available now 1 to 6 kilograms. Sam can support me here, I think.
All the way up to 4,000 kilograms an hour.
Yeah.
But from air, we don't any longer do anything below 15 kilograms an hour.
You don't? That's
Then
what I should
the
do.
payback isn't there
Okay.
on the capital investment.
Would they still make you one if you wanted to?
You could, but you would not receive a payback on the capex.
No. Okay.
The cost of that, the energy cost
Yeah.
of putting it input is more
Yeah.
than production.
Okay, and they talk about purity in excess of 99.9 and 100% food grade CO2 from known source. So basically it's providing everything you need for the plant. So in conclusion, is the carbon dioxide recovery plant right for my brewery? If you're in business for the long haul and fluctuations in the availability of CO2 and advances in CO2 technology, they're now available for your size brewery, whatever. If you're, say, above probably what, 10,000 hectolitres per annum, something like that. And if below that, you're borderline, maybe keep buying from there, be clean somewhere. It can help you maintain a robust supply of CO2, be more environmentally friendly and financially viable. You're not chucking the CO2 into the atmosphere, so the greens won't be on your back. You know, you're collecting all the CO2. I know that Carlsberg did an exercise, I mean I'm talking 20 odd years ago, where they reckoned that the amount of CO2 that's mopped up during the growing of the barley and the hops and everything else balances out the amount of CO2 you produce by brewing your beer. So I think, you know, overall we're pretty okay. But everyone sees our brewery must produce CO2, must go to atmosphere. At least now you can collect it, get them off your backs. So I think it's worth seriously thinking about installing such a plant. And I'd like to give my thanks to Pentair, Dallin, Hypro and others for the information used in this presentation. Here's my references. That top one I think is well worth looking at. I don't know what's going to happen to these slide packs. They're going to go out to people if they want.
Slide deck's going out to everybody.
Good. So that one there, I say, Jaime Hardo's a brewmaster, a master brewer. He used to say chairman of the Master Brewers of America for a couple of years, and
It's currently in Alaska.
yeah, that's right. I saw that. Yeah, yeah. He's been around. I worked with him at Shiner Brewery in Texas. I remember coming with Shiner Bock, the famous American beer. That was one of his. Pete's Wicked Ale. So yeah, he's been around a bit. So the first key American consultant, or Canadian consultant, they did a looking closely at CO2 recovery at your brewery. That's quite a good paper to look at. And then there's the Hypro Galleria, as they call it. There's lots of nice pictures and links to their website. And I could have put Sam's up there as well. I don't know. But you know, I think it's
the same
well
as
worth
ours.
looking at. Okay, that's it.